we will discuss now directional control. Okay. Now elevator we have done in longitudinal case, aileron for the lateral case, and now last one is rudder. This is primary aerodynamic control surface, elevator, aileron and rudder. So rudder, okay. So if the rudder is deflected in this way, my thumb is pointing downward, right? So my deflection will be considered as a positive towards this direction. That means rudder is deflected in this direction, so it is positive, and in this direction negative, right? So if your yawing is happening in this direction, you have to deflect the rudder in opposite direction, this direction, to generate the vertical force in this direction and counter the same. So this one is a positive and this one is negative. Okay. Positive, negative. Okay. Small n yawing moment minus L V into LV. This you can write half rho V square S B Cn, and this you can write half rho Vt square SV, and then lift coefficient that you can write in terms of vertical lift slope, and since you are deflecting the rudder, you will write tau into delta R, this into L. This we have already seen how to convert the lift coefficient in terms of control surface deflection in lateral and longitudinal cases. Okay. Now you can further write Cn is 1/2 rho v square Vt divided by half rho v square is eta V, and SV LV divided by SB, which is vertical tail volume ratio, CL alpha of the vertical tail. Okay, and here you will write tau, and this is delta R. Okay. Now differentiate with respect to delta R. Please note down this. Okay. I have written yawing moment half rho square SB into Cn. Cn is yawing moment coefficient, and then minus half rho Vt square SV. I have just spanned the LV, and then what is the lift coefficient coming? I have written in the control surface deflection in terms of control surface deflection, and then into LV divided by, I have divided half rho square, and then you can see half rho square Vt divided by half rho square eta V, and then SV LV divided by SB is VB, tau CL for the vertical tail delta R. Fine. Now if you differentiate with respect to delta R, you will get Cn delta R, which is minus eta V VV tau CL alpha of the vertical tail. Okay. Are you aware of this? Cm delta E minus eta VH tau CL alpha of the tail. I already explained this, right? In longitudinal case, right? It is same only, right? It is same. Eta V volume ratio. Okay. See, control derivative. Tail efficiency factor. Tail volume ratio. Tau. Lift curve slope. Only just in this case it is horizontal tail, and in this case it is vertical. So you can see exactly what doing. In horizontal tail, you can see horizontal tail and putting the support. You can think in that way, right? So expression is same, right? So what is the job of the directional control? First thing is, for example, like if you are rolling, okay, you are rolling the aircraft. by increasing the lift here and decreasing the lift here. And if the lift is more here, the drag will be more here. If the lift is less here, drag will be less here. So that differential drag will try to yaw in this direction. But since you are rolling in this direction, so you don't want this motion, right? So what you will do? You will deflect the rudder in this direction to counter this yaw. That is how you will achieve the coordinated turn. Without side slipping, you are rolling the. That is the one job of rudder. What do you think can be the other job? Let's say commercial aircraft is flying, two engine, right? If one engine is fail, so what? Thrust is coming in this direction, right? So if this engine fail, this will try to take a yaw, right? So you have to counter that yaw. So you have to deflect the rudder in this direction to generate the force and counter the same, right? Okay. So in this case also, you are using the rudder at a asymmetric thrust condition. One engine fail or one engine is partially working, not producing the thrust as you want, less thrust. Then in that case you can use two best use I have told you, right? Your aircraft is stalled, so you are not producing any lift, so your altitude is losing, and at the same time you are yawing also, and that yaw rate is more than compared to the roll and pitch rate. That phenomena is known as a spin. So in this case, to stop the spin, you can use the rudder. Okay. So there is like many cases where the rudder is very important, and one more important case, for example, you are in a situation where the crosswind is coming and you want to land the aircraft. So in that case, okay, you can handle the side slip angle. For example, like in mathematically also you can see Cn is, you can write Cn beta into beta plus Cn delta r into delta r. So if you want to make no yawing moment, okay, so Cn delta r into delta r you can write, and delta r you can write minus Cn beta divided by Cn delta r, okay, into delta r. Beta. Okay, this case simple. I don't want to. I will use rudder in a, to kill my yawing moment, which is coming from the, let's say, side slip. Okay. Now Cn beta is what? Already positive. Cn delta is negative. So negative will be the positive. Okay. So if your side slip angle is what? Side slip angle is sine inverse V by capital V. Okay. So let's say some your aircraft having velocity 30 meter per second and the crosswind 5 is coming. So can you tell me what is the angle? Sine inverse 5 divided by 30. Can you tell me the answer? What is the beta is coming? 9.59 degree, right? Your beta is coming, right? Let's say Cn beta is 0.01 and Cn delta r is also 0.01. Okay. So what will be the delta r? It will be this is minus sign. Okay. So this will be 1 into, let's say, beta. So beta, what is the beta is coming? 9.5, right? Okay. Delta r. So delta r, how much is required? Approximately 10 degree. Positive, right? So positive which direction? Which direction is called positive? This direction is positive, right? Okay. This direction is positive. So if you deflect the rudder in this direction, what kind of motion will happen? This motion, right? This. Okay. So consider this scenario. What I have taken? Wind is coming 5 meter per second. Let's say crosswind 5 meter per second is coming, and direction is positive, right? Okay. So that means aircraft will try to take a yaw. It will try to have a side slip like this. So if you do the side still like this and you are landing, then you will not touch at the landing center point, right? You will skid, right? But if you deflect the rudder in this direction, which is coming on 10 degree, you will counter the yaw and you can land your aircraft. Okay. So that is the importance of a rudder as a directional control. Okay. So this is all about the directional stability and directional control. Thank you very much.